All right, so today we're talking about the very last section in Chapter 7, which is Section 7, Modeling with Exponential and Logarithmic Functions. So the first thing we'll look at is classifying a set of data. So basically we're going to look at the table and determine whether it's a linear function, a quadratic function, or an exponential function. And the way that we'll do that is by looking at the y values. Now we've already talked about how to identify data sets if they're linear or quadratic, and that's when we count the difference from the y's. If it's the common difference or the same number all the way across for the first difference, it's linear because it's a first degree, and if it were the same difference the second time across, it's a quadratic and it's second degree. So let's first look at an example that's a review, and then we'll move on to the new type, which is exponential. So for this first table, looking at our y's, from 2 to 0, we have to subtract 2. From 0 to 2, we have to add 2. From 2 to 8, we add 6. 8 to 18, we add 10. And then 18 to 32, we add 14. So we know that this isn't linear because this first difference is not the same number all the way across. So we'll try counting it again. So from -2 to +2, we add 4. From +2 to +6, we add 4. From +6 to +10, we add 4. And from 10 to 14, we also add 4. So since we got a common number or a common difference the second time we counted, that means it's a second degree function, which makes it quadratic. Now, what if you counted the difference twice and you still didn't get the same number? Well, then you'd want to look and see if it could be exponential. With an exponential function, instead of finding the difference where we add or subtract, we're going to figure out what number we have to multiply by each time to get from each y value. So looking at this next table, you have to think about what number do I multiply 27 by to get 9? And the way that you could figure that out is take 27 and then divide it by 9. So 27 divided by 9 is 3. So I have to divide 27 by 3 to get 9. The other way, if I wanted to write it as a multiplication problem, is that I would multiply it by 1/3, which is the same thing as dividing by 3. And let's see if this multiply by 1/3 works for the rest of the table. Does 9 times 1/3 equal 3? In other words, does 9 divided by 3 equal 3? Well, the answer is yes. And then again, does 3 divided by 3 give you 1? Yes. Or 3 times 1/3 gives you 1. And since for these y values we're having to multiply by the same number all the way across the table, that makes it an exponential. Again, adding or subtracting, quadratic or linear, multiplying, exponential. So let's look at this next example. From 1/9 to 1/3, what did you have to multiply or divide by? And if the fractions are too confusing, come up here and pick a different number where it's whole numbers and it might be easier to see. So like from 3 to 9, what did we have to multiply it by? Well, we multiplied by 3. So let's work backwards and see if that works for the whole table. Does 1 times 3 equal 3? Yes. Does 1/3 times 3 equal 1? Yes. And then 1/9 times 3 equal 1/3? Well, yes, because 3 times 3 gives us a 9 in our denominator. So again, since we multiplied by the same number all the way across the table, this is also an exponential. Last one. If you look at your y's, each time we're only decreasing a little bit, so let's see if it works with the subtraction or adding. So from 15 to 12, we subtract 3. From 12 to 9, we subtract 3. And from 9 to 6, we subtract 3. And since we got the same number all the way across the first time we counted, it's a common first difference, which means it's first degree, so it's linear.